Hi, everyone. I'm Molly James. I am a PhD student at the University of Connecticut. I'm also a physicist, but not of space, but of the ocean. So it's my pleasure to introduce Dr. Lachlan Lancaster. We know each other. We went to high school together. Lachlan went to Carnegie Mellon first and got his Bachelor's of Science in Physics, then went to England to pursue a master's at Cambridge University, then came back and did his PhD and another master's at Princeton University, and is now currently a junior fellow at the Simons Society of Fellows at Columbia University with Professor Greg Bryan, studying star formation. Tonight, he'll be talking about dark matter and dark energy. Without further ado, Dr. Lachlan Lancaster.
Thank you so much, Molly. Thanks so much for having me. It's really, really cool to be here. What are dark matter and what are dark energy? These things, as we will sort of get to, these things are really sort of placeholders for things that we don't understand. And I think that's partially why they're also interesting, why people like thinking about dark matter and dark energy. They're kind of sort of these things that we can't understand. What are these things that we call dark matter now or dark energy now? And why do we think they're real? It was controversial still, but throughout the 70s into the 80s, people finally came to understand that dark matter is a real thing. Dark energy, what is our evidence for dark energy? So Hubble showed that if you measure the velocity of galaxies, the further away they are from us, the faster they're moving away from us. So that showed that the universe was expanding. In 1998, these three physicists who led teams of, I should say with all of the people that I'm talking about, almost it should be implied, but they're not the only person who did the work. There is usually a lot of people that goes into the discussion. And so I'm a little bit contributing to this idea that science is only done by sole geniuses, which is definitely not the case. But it's an easier story to talk about, which everybody thinks that it's just these sole geniuses. But usually there's huge teams of people behind it. And that's definitely true in this case. So in 1998, these two separate teams announced results that showed that not only was the universe expanding, but its rate at which it was expanding was actually accelerating. So it's expanding and it's speeding up in its expansion. I'll just say that beyond those things that I talked about, which were sort of the first evidence for dark matter and the first evidence for dark energy, since the early 2000s, we have lots of great probes about structure in the universe, basically how the universe is held together. One of the best ones of those is the cosmic microwave background. This is what is very nicely called the afterglow of the Big Bang. So in the very early universe, the universe was very, very dense. It was so dense that light couldn't get very far without bumping into other things. It was very, very dense, this very, very hot, dense plasma. But as the universe began to expand, eventually that light that was running around and hitting things got low enough density that the light could escape and free stream off. Yes.
How do you define universe?
For the purposes of this, I will restrict to the observable universe, things that are within things that we can observe. The boundary of which is this, pretty much. It's a little bit weird to think about, but this radiation is coming to us from the other side of the universe, where it stopped free streaming a long, long time ago, and then it's just been traveling across the universe until it gets to Earth, and it finally hits a detector and we detect it. The question was, you just defined the universe to be the things that we can observe, but you've also said that dark matter and dark energy are not observable. Therefore, are they part of the universe? I would say that the effect that they have on the universe is directly observable. I'll say the indirectly observable universe, and in that way, contain all of dark matter and dark energy in that. So this is basically the afterglow of the Big Bang. It's when the universe expanded, eventually light was able to escape, and that light has sort of eventually gotten to us. Well, first of all, everybody sees this red right in the middle. That's just emission from our galaxy. So that's not, that doesn't have anything to do with the cosmos. And that's the main foreground rather than background to observing this cosmic microwave background. This radiation is now in the microwave band of radiation. But there's lots of emission from our galaxy, which is very relevant to the sorts of stuff that I actually study, which is more like our galaxy. But for the cosmologists, this is totally annoying. So they do their best to remove all of that information and they basically look at the top and bottom of this picture. But all that fuzziness that you see at the top and the bottom of the picture, that's sort of telling us about the structure in the early universe, and a lot about how that light traversed the entire universe to get to us. It's called a power spectrum. It's basically a statistical measurement about the properties of the fluctuations in that map. So it's just a way to measure on what scale there is structure in those maps. You can use Einstein's theory of general relativity to predict what you would expect to see within this measurement. And in order to match the data, you need to include dark energy and dark matter, the line in the back. We now understand what we think about when we say dark matter and dark energy. Why are these things that are necessary in our understanding of the universe? But I haven't said almost anything about what they actually are. And the fun answer is we have no idea. But anyway, I'm going to talk about some things that we think that they might be, and why or why not they're good candidates. Dark matter. There are multiple possibilities here. We have this dark matter. Is it actually missing matter, or is it that we don't understand gravity fundamentally? It doesn't necessarily have to be that there's this missing matter. It could be that there's something else. So let's first go with the second thing, which is maybe we don't understand gravity. And in the 70s and 80s, when this stuff first was proposed, people came up with, they're like, what if we just change the force of gravity a little bit? And in particular, we say that all of our tests of gravity act in this regime where the acceleration due to gravity is quite strong. But what if gravity changes when you go to this very, very weak acceleration regime, which is where these observations happen for these galaxies? And you can come up with some math that reproduces the velocity curves of these galaxies and reproduces the velocities of galaxies in clusters. But there is no, what we call relativistically complete. There is no theory in which you can get Einstein's field equations to work and this to work in a way that also is consistent with all of the other tests of Einstein's theory of gravity. On top of that, you need something like that in order to reproduce the large-scale structure of the universe and the predictions from the cosmic microwave background radiation. And this doesn't do any of this. So despite that, people still think about this a lot. There's probably a paper on the archive is this preprints website that I go to look out for new papers. And there's probably a paper on Mond every other week or something. Not everybody has accepted it. I think that's good. You should keep asking questions about and thinking about these things. But right now, it seems like this is not the right way to explain this dark matter problem. So coming back to the missing matter, so that was changing our theory of gravity. That's the only even feasible thing that we've thought of for doing that. So now let's think about what's the missing matter? What are these things that we could be seeing? The first thing that you might think is that this stuff is things that we already know about. So in general, if you're Aristotle, you say, look to the things that we understand and use that to explain the things that we don't understand. Definitely the first thing that you should do, right? And we knew at the time throughout the 20th century that there are black holes that are crazy, but they're a thing. There are neutron stars, which are basically the remnants of stellar evolution. When stars die, they leave behind these things. And they could be sitting in galaxies, and we can't see light from them because they're dense enough that they're just sitting there. In order to reproduce the observations of these velocity curves, you need to estimate the density of these things. At the density you need to reproduce the observations, then these things should also lens background stars. So you get the same thing. That's what's being shown in this picture on the left of a black hole to an extreme degree. But if you have a bunch of these objects sitting in our galaxy, every now and then they should fly between a star and us. And when they do that, the star should get brighter and then dim. It should, because the light is lensed towards us. And with all of these huge digital sky surveys, we observe a lot of stars all the time, and we don't see this. That sort of rules out the lower mass ones, and the really high mass ones would basically destroy galaxies. So they can't be around either. So these are not favored objects. This tells you that astronomers and physicists have a sense of humor. So we had machos I guess it was mostly the particle physicists who came up with this, but they said, what if not having the massive compact halo objects, machos will have weakly interacting massive particles, WIMPs. And this is basically a particle that lives a little bit beyond the standard model of particle physics. It's sort of naturally predicted by some supersymmetric field theories that are basically sort of extensions to the standard model of particle physics. But this is still I would say, our best candidate for what dark matter is. But there have been tons of experiments designed to find these things, tons of experiments to find things having to do with supersymmetric field theories. Neither of those things have borne any fruit at all yet, which is sad. But they also haven't ruled all of the interesting parameter space out. So this is still our best candidate, I would say, for what dark matter actually is. But even though that's our best candidate, there's some more fun ones. So let's talk about massive neutrinos. Again, I should say that WIMPs, this is appealing to something that we don't know about. This is inventing new physics in order to understand the things that we see, rather than explaining it with things that we do see, or do know that exist, at least. That's part of the reason why it's hard to disprove, right? Because there's always more parameter space. So that's why it is okay, I think, to sometimes question whether that's scientific anymore. If your theory is not disprovable, then it's not necessarily science. But that said, it's still sort of our best candidate. This is other stuff. This is stuff that lives within the standard model of particle physics, neutrinos. Neutrinos are very, very weakly interacting particles, and they have very, very small masses. One of them, there are three of them, and one of them might have a pretty large mass. And if it has a large enough mass, it might be able to explain some parts of the dark matter, but probably not all of it. So those are just normal neutrinos. There are also things called sterile neutrinos, which are sort of a normal addition to the standard model of particle physics, but we don't really have any real evidence that they exist. They could also be some part of this dark matter problem. That's the other thing with understanding dark matter, is like there's all this missing mass. Does it all have to be one thing, or can it be a combination of a bunch of different things? So these things could contribute to that picture. The final thing that I wanted to talk about, I worked on it, so I'm going to talk about it, is so-called fuzzy dark matter. The WIMPs, they have a few problems on small scales, cosmologically small scales, galaxy scales, having to do with the dynamics in very dense regions that should probably be totally explainable with star formation, the stuff I actually study. Usually when there are problems like that, the physicists who want to understand dark matter will invent something to explain some observed problems. And one of the things that they did was to say, well, what if dark matter is so light, the particles are so light that they act quantum mechanically on astrophysical scales. So this is like several tens of orders of magnitude lighter than an atom, like super light. And there are some things in string theory that might predict something like this. And to show you that, this is sort of the video that I'm showing, which is from a collaborator of mine, Dr. Philip Motz. It basically throws a bunch of these sort of dense things together under the equations that would be applicable in this sort of weird theory of dark matter, sees what happens. So you can see these things, let's see if that goes, slowly fall into each other, and then they excite waves. This is where the fuzzy fluctuating part comes from. And that is those are basically quantum fluctuations happening on astrophysical scales. And it gives you all these fun little fuzziness, this background in the galaxies. The problem with this model is that those fluctuations in the density, which are sort of inherent, they have to be there if this fixes the small scale stuff that you want to fix. They also destroy galaxies. They heat it up through motion, fluctuations in the density of the background stuff. And so you can't have cold disks of galaxies that we observe with this. That's dark matter. I sort of explained some of the theories that we like to understand or want to use to understand that. Finally, what is dark energy? So again, we have a picture where do we appeal to something completely new, or do we try and use things that we think we understand in order to explain this? The first thing, vacuum energy, is sort of trying to use things that we understand in order to explain this. In particular, due to quantum field theory, which is a thing I haven't talked about at all, but sort of was developed throughout the 20th century, space itself should have some energy, which I can't get into explaining, but just believe me that is true. If you use our standard model of particle physics to predict what the energy of empty space should be, then you are off by what the cosmological constant needs to be by 120 orders of magnitude. So not only does this not explain the cosmological constant, it also leads us to the other question was, well, if this is right, then why are we not expanding even faster than we are before? So in order for the standard model of particle physics to be correct, and for this vacuum energy density calculation to be correct, then we need some other stuff that we don't understand to perfectly cancel out this 120 orders of magnitude almost perfectly, but not quite. So this is sort of like the most spectacular failure of theory, I would say. So it's not that. That's sort of the end of the list. There is some laundry list of very esoteric things that I probably could have gotten into, but they take a long time to explain and they're not very elucidating in anything, really. So I would say that basically you're left with this cosmological, changing gravity in order to understand where this comes from. But this is sort of just out of the hat. We don't understand what dark energy is. Keeping in mind, again, the history of things that we've seen in the past, like we could be completely off base here and we won't maybe realize for a long time, right? It was 100 years between Newton and just Leverrier, or even 200 years. And between Leverrier and Einstein, another 50 years or so. And it's 100 years since Einstein again. It's only 20 years since we discovered that dark energy should be a thing. So these things take time to understand. So conclusions. So I've talked about things we don't yet understand in physics. They're basically what I was just saying. But the other point I guess I wanted to get across is that if something is science, if we're asking these questions, the questions that we're asking, they have to be, or theories that purport to explain those things, they need to be testable, they need to be provably wrong, or else it's not science, it's not a scientific question. And it's unfortunate that these days we seem to be running up to these, or at least it seems to me like we're running into these things, but maybe that's how they felt back in the day too, that we're running into these questions that we find hard to explain. But there's a lot of open questions here, and there's a lot of ongoing work in all of these. I've really only touched the very basic surface of all of these things. So there's a lot more to do, which is why everyone should pay their taxes and we can keep doing a strong. I'll leave it there. Thank you very much.